Hello, everybody. Many thanks for joining us for what promises to be a fascinating discussion. I'm Lucy Craig, and I'm Vice President of Technology and Innovation in Energy here at DNV, and I'm your host for this session. The offshore wind industry is, of course, very well established, but we're going to focus in this session on an emerging and hugely exciting development within the industry, floating offshore wind. I'm joined by some expert guests who go into more detail on exactly what floating wind is. But in its simplest terms, it's a way of allowing us to harness the significant potential of wind power available further offshore than fixed turbines can reach. DNV projects that floating wind will grow to reach a total capacity of 250 gigawatts by 2050, making up about 20% of the total installed offshore wind capacity and around 2% of the world's power supply. In this discussion, we'll explore the vast opportunities that this emerging technology presents, look at what's standing in our way in terms of maximizing its potential, and look at the key challenges we face in reaching commercialization. We'll also examine how we can take learnings from fixed offshore technology into this brand new area, the countries we see leading the way in floating wind development, and the importance of policy intervention in driving it forwards. There's a lot to discuss, so without any further delay, let's begin. I'm going to start by talking with Henrik Stiesdal. Henrik is CEO of Stiesdal Offshore Technologies and is one of the pioneers of the modern wind industry. He built his first wind turbine in 1976 and in 1978 designed a commercial turbine that was then licensed by Vestas. During his more than 40 years in the wind industry, Henrik has worked with all aspects of wind turbine technology, from fundamental research and turbine design to project implementation and quality management. The wind industry has developed dramatically over these past 40 years, and I'm really interested to get Henrik's take on how things have developed since those early days. So Henrik, thank you very much for being with us. You've famously talked about some of your earliest work on wind technology and how that took place while you were sitting at your kitchen table. Can you tell us about your early discoveries and why they were so important in creating the wind industry we know today?
Yeah, of course, I was super lucky in being involved in the early days where things got off on what turned out to be the right footing. There were at that time in the mid 70s onto the late 70s a quite wide range of people in Denmark who were really interested in wind power as a means to gaining energy independence. Nowadays we think mostly of wind as a way to avert climate change, but in those early days it was all about the aftermath of the oil crisis, where Denmark, without any natural resources, had been terribly exposed to the development in the Middle East. And I became part of that sort of small community with people living in different parts of the country and communicating about it. And it was super exciting. I was a very young man at that time with no engineering background or anything. And the wonderful thing about wind power was that it was difficult, but not too difficult. You could actually get involved in aerodynamics, or you could understand how a gearbox would work, or you could inform yourself about how to make structures if you had a certain interest in technology. And it always had this really sort of tantalizing element that the more you learned, the more you could do and the more we could develop. So they were really interesting days.
Thanks, Henrik. Can you explain some of the big milestones that have taken place in the wind development since those very early days?
Yes, of course, we have gone through an interesting trajectory that is actually not that different from many other industries, in the sense that we started out with a wide range of choices. You could do 2, 3, 4-bladed machines, you could do upwind machines or downwind machines, you could do all kinds of different things. And then gradually, as we all know, a winning technology has emerged. For us in Denmark, in the sort of pioneering community, we looked very much at what had been done in earlier decades in Denmark, long before the oil crisis. And out of that came a sort of shared perception that the 3-bladed upwind wind turbine would most likely be a good bit for a winning concept. That came more or less by itself. Something that did not come more or less by itself, but which turned out to be hugely important, and which, quite frankly, I think most people either have never heard about or have long forgotten, is that in the early days, wind turbines relied on mechanical brakes for shutdown. And if something would go wrong on a mechanical brake, you could have a runaway of your turbine, and that could lead to blade throw and a total collapse of turbines and so on. I think actually I still have the Danish record in blade throw. I've thrown a 5 meter, 75 kilogram blade, 475 meters, which I don't think anybody ever did longer than that. Some people have thrown fragments of blades longer because they were carried by the wind. And I may be able to make it sound as if it's entertaining. It was not particularly entertaining at the time. And therefore we ended up developing air brake systems that would ensure that turbines could never have a runaway, so that there would be a part of the blade that would deploy as a brake system. That was actually a genuine breakthrough, because what we worked with turned from being something that was potentially dangerous to something that was safe. That was a major thing. The other major thing, of course, was that due to the combination of the way that the Danish government ran subsidy schemes and the fact that the California market boomed in the early and mid 1980s, we got volumes. It was actually the volumes that created the industry. It was the market pull, the fact that you could actually go in and have genuine turnover and so on. Very often when you speak with people who look at our industry, they focus a lot on the technology development. And of course, it has been full of technology, this magnificent growth in turbine size and more advanced regulation mechanisms and what have you, direct drive generators and so on. But what has really driven the cost down is actually the industrialization that comes with volume production. And that is really a key factor also when we speak about the future. That is that we need to seek solutions that allow us to make genuine mass productions. And there the wind industry, quite frankly, was lucky. It was lucky by being built up by a subsidy scheme that was favorable to creating a market, and it was super lucky by getting engaged in California and actually seeing wind farms of hundreds of turbines materialize over there.
Thanks, Henrik. We're really focusing now on floating wind, which has developed very rapidly over the past 10 years or so. So for the benefits of those who are joining who may be unfamiliar with the concept, can you tell us exactly what floating wind is and how it differs from bottom-fixed offshore wind installation?
Interestingly, offshore wind was spoken a lot about in the 1970s and early 1980s. And it was only when we had the California boom that all the focus then went on onshore wind. But nobody really did much about it until around 1989, when the Danish government decided to promote 2 demonstration projects in Danish waters. And I had the very good luck to be involved in the first of those in 1991. So this year we will have the 30-year anniversary of the very first offshore project. The reason for that was that it was acknowledged that over time there could be a space constraint on land. And that's of course why we looked at offshore wind power and why that came in. And it has been this tremendous success we all know about. And we all know that the EU is now expecting to get 50% of its electricity from offshore wind by 2050 and so on. So what more could you ask for? But it has the big drawback that offshore wind, as we know it, has been developed and become an economic success in what is essentially an anomaly in the world, which is large areas of shallow water close to big population centers. Unfortunately, most of the world is not like that. There are other parts of the world that are like that, such as the eastern seaboard of the US, outside New York and Massachusetts, Jersey, and so on, and also on the coast of China. But most of the world does not have the luxury of having big areas of shallow water close to population centers. And that's, of course, where floating wind power comes in. That is that we say, well, we have this technology, it's got everything speaking for it. It's just dependent on, in its present form, that the water can be no more than 60, 70 meters deep, because if it gets too deeper than that, then the cost of the foundation becomes prohibitive. Some even say 50 meters is going to be the limit. And that is where this idea, which is really as old as the whole discussion of offshore wind, to simply say, well, then they don't stand on the seabed, then they float and are just kept in place with mooring systems, that comes into play. And the effect of that is actually very dramatic. If you look at a study that IEA did about a year ago, they conclude that bottom-fixed offshore wind can supply on the order of the full electricity consumption of the world. And there was a super, that's great, that's what we need. We need what we consume. But unfortunately, that is located in a limited number of countries or outside a limited number of countries. And unfortunately, we're going to need a lot more electricity in the future because we are going to do power-to-X fuels and use electricity for all kinds of industrial processes that are now run by fossil fuels. If we add the potential of floating offshore wind, we go from being able to supply the full electricity consumption of the world today to being able to supply 10 times the full electricity consumption of the world today. And furthermore, we are going to be able to serve a lot of countries that cannot realistically be served by conventional bottom-fixed offshore wind because it simply gets too deep, too close to the shore to allow for that.
Yes, thank you. And as you mentioned, with floating wind, there's possibility to tap potential that there is where there is greater water depth. And you described very eloquently earlier on the technical developments and also the commercial developments which have driven wind in general. When it looks to floating wind, we're now seeing those early commercial projects. So what have the technological developments been to get us to this stage where we're now able to exploit that huge potential?
I think that you can say that the most, it's a bit like when we did the turbines originally. There were no end of plans. There were no end of drawings existing. It only really got traction when we got machines up and running. People were speaking offshore for decades. It only really got traction when somebody, in this case the Danish government, it could have been somebody else, sat down and said, now we actually want it to happen. And the projects were actually built. So the real, what shall we say, credit for making floating offshore wind happen belongs to people and companies who were the pioneers in doing it. The very first project was built by Equinor in 2009. The next was built by Principal Power together with the Portuguese power company EDPR in 2011. French company Ideol came in later. We had a number of demonstrators installed in Japan, the Fukushima project, and so on. And that's really what made it happen. What people tend to forget today is that in the early years, we actually did not know for sure whether there would be issues in going to floating. And the main concern we had was whether turbines would become unstable, so that due to their response in the wind, they would have a self-excitation mode in the wind and would drive big excursions of the floating system. And that was resolved with the very first one, the one that Equinor built, the Hywind project in 2009. I was involved in supplying the turbine for that project, and we installed a motion control system in the turbine. And Equinor had their own system, and we simply tested out these different systems. And the observation was that in high wind speeds, there was actually something to the concern about self-excitation. Not so that the turbine got to be unstable, but it was lively. When we then installed one of the motion control systems, it got to be completely stable, solid as a rock. And that was a major milestone in this. And the credit for us being able to sit here today and discuss the volume of so many hundreds of gigawatts of floating offshore wind actually belongs, of course, both to the big research community and to the turbine people wanting to do stuff like that, but it belongs also to the people who actually made it happen. And they're the first and foremost players, Equinor.
Thanks, Henrik. And I have one final question, and that is about, of course, we've got these early commercial projects now which have been enabled by these pioneering companies. And we see huge potential over the decades out to 2050. But what do we actually need to do as an industry to get to that wide-scale implementation of floating?
In my opinion, it's of course a long story. But you can say that if we look at the experience from the bottom fixed industry, it only really took off big scale when it became a competitive and financially investment attractive industry. And in order for it to become competitive, what we needed was volume, serial production. We needed to take it to something that was done at industrial scale. And there is, of course, a sort of chicken and egg thing, because if you don't get a market pull, you don't get enough built. If you don't get enough built, you don't get the industrialization and the benefit of mass production. So there is, we are, of course, hoping for early ramp up of projects. And then we as an industry need to do what we can to industrialize, so to speak, deliberately as early as possible, so that we make sure that our solutions are well suited for low cost production. And then we need to make sure that it is sufficiently financially attractive. And that comes, there is a certain inertia in a financial system. The bank's engineers would want to see proof that big projects can be built and can be demonstrated and so on. And there we will have to rely on some early pioneering developers that build projects, and they will create this financial credibility. Of course, we benefit from having a very big financial credibility in conventional offshore wind. I remember very clearly that until about 2012, the basic tone of questions was from banks and from investors and so on was, you need to convince us why we should invest in this. And from about the change of year 2012, 2013, it flipped. From 2013 on, the question changed to, do you have another project we can put investment? And that same thing we need to pursue actively. And then finally, of course, the whole ambience needs to be prepared for what we do. And that means that we need planning conditions and ways of discussing fishing interests and bird interests and whatever else you have as we could think of secondary things. But of course, they are very real things for the people involved in a rational manner. And there I myself am engaged with the Global Wind Energy Council that does kind of support work for governments in order to make them understand how can you make this happen. So it's a mix of the technology providers. They need to think industrialization and mass production into their solution in order to get the cost down. It's a matter of developers taking these first steps and doing projects that can act as lighthouses for investors. And then it's a matter of governments and regulatory bodies and others to get engaged in saying, we actually would like this to happen. It's a big future for the planet. This is one of the solutions, one of the sort of key solutions in many parts of the world to give us the larger volumes of electricity we need in the future. We as governments or regulatory bodies, we want that to happen. Let's see how do we go about making it in a rational manner. So it's a mix of these different elements.
Thank you very much, Henrik. It's been a really exciting journey so far, and it's clear that there's a lot more to do, and a matter of putting all these different building blocks in place to achieve this huge potential. I'm very pleased that you'll be back to join us in about 30 minutes for our live Q&A with our audience, and so I look forward to speaking with you again then. And for now, we'll move to the second part of the session. Thank you. So there's lots to discuss then, and without any further delay, let's meet our guests. Sebastian Bringsvaart is head of floating wind at energy company Equinor, who established the world's floating offshore wind project, Hywind Scotland, off the coast of Aberdeen. This installation is fully operational and provides power for homes in Scotland. The company is working on a second major installation, Hywind Tampen, an 88 megawatt project, which is intended to provide electricity and the first one that will provide electricity for offshore field operations in the Norwegian North Sea. Wei Chen is General Manager of the European Business and Engineering Centre at turbine manufacturer Mingyang. The company is headquartered in China and established its European base in Hamburg last year. Away from Europe, the company is going to supply the turbine for China's first tender for a floating wind deployment. Wei is also a former renewable certification engineer here at DNV, so we know each other well. And finally, but by no means least, Magnus Ebbesen, who is business lead for floating wind here at DNV. Magnus is part of DNV's cross-industry task force on floating wind, which encompasses several of the company's divisions, including power and renewables, oil and gas, and maritime. Magnus has conducted floating wind market and cost studies for many of the leading floating wind developers, and he has a holistic view of how the technology is being implemented globally. Sebastian, your company Equinor established the world's first commercial floating wind project in Scotland, which has been hugely successful and powers homes on the Scottish mainland. What technical challenges did you encounter, and how do you think the lessons learned can be adopted as the technology is implemented globally?
Thank you, Lucy, and thank you for those nice words, and thank you for inviting me to this talk. First of all, Hywind Scotland is the first floating wind farm globally, and it's a small one. It's 30 megawatt, but still it's hugely important both for Equinor and for I think the floating industry in general. Powers roughly 20,000 homes in the UK and is the best producing asset in UK. Capacity factor wise, and obviously that is because floating wind can harness the best winds out there, but it's also a very important point to say that it is really, from a technical, operational, safety point of view, equally reliable as any bottom fixed wind farm. So I think that's important fact, and that is actually taking us to what Hywind Scotland is. It is really going from pilots and technology testing and innovation to what floating can become. And as your ambition for where floating would be in 2050, I think it is an important, small but very important stepping stone. It is what we have tested here or done is basically building a small wind farm, and it shows that by doing that, we are really proving the concept in a wind farm configuration, which is hugely important for us. I think the biggest challenge with the project, or the biggest learning, has not been one particular item or one particular process or technology to make it work. It is really to understand how this integrates. It is familiar technology from oil and gas to have a floating platform or a floating structure. The turbines are known technology from onshore and offshore wind, but it is really about putting it together and make it work, and it does. So I think that's kind of where the biggest learning and an area for us in terms of experience from a project perspective, how to integrate this, how to make it one producing asset that really are functioning. And on a project level, I think the whole logistics and testing out how to manufacture, fabricate, install, and then operate has been the kind of important learning for us, and it is really what we take forward when we need to go in on industrial commercial scale, which is the kind of next step in the floating story.
That's fascinating. So, thank you very much, Sebastian. Magnus, building on what Sebastian has told us, how important are these early commercial projects and pilots in demonstrating proof of concept for floating wind? And perhaps, if you'll allow me a parallel question, who are the stakeholders that we need to convince of this huge potential in floating wind?
Thank you a lot for that question. So these wind farms are very important. I think there are like three main aspects we get from this project. They provide confidence to the industry that the floating wind works, that we're actually basically able to integrate all those things we know from other industries into a project, as Sebastian told about. They show that costs can go down, and they also bring the lessons learned. So when we talk about the confidence part, this project is installed today really show things works. Look at the two first floating wind farms, Hywind Scotland, Wind for Atlantic. These two wind farms have completely different climate conditions, different market and regulatory schemes, different turbines and OEMs, different financing structure, different developer background, and last but not least, different floating wind technologies with the spar and the semi-submersible. And both are now completed and proves it can be done. And also looking at the capacity factor, which has been communicated from Equinor, which has been really high from Hywind Scotland. This really shows that floating wind is not holding anything back compared to bottom fixed with regards to energy production. And when we're talking about cost, these first floating wind farms play a role to show that we can get the cost reduction, as we have a way to go on cost. And I think when we're looking at the wind farms that will come in not too far in the future with 100 to 200 megawatt size, I think we will get evidence that we are on the cost trajectory we hope for. And last, I believe there are tremendous learning from these first projects. These first projects that have been installed and the next round of wind farms will contain a big part of problem solving and lesson learned. And I'm sure the parties involved, such as Equinor and others, have learned a lot on how to build floating wind with lower risk to a lower cost. And also talking to ourselves in DNV, who has been involved in many floating wind projects, we can also say that we have learned a lot. As an example, we have been a lender's technical advisor for Wind for Atlantic for European Investment Bank and followed that project for years. And we have definitely learned a lot about putting theory into practice. And I believe these learnings from this has been beneficial for other financiers we have worked with after. And as another example is our role as certification body for Hywind Scotland. We got the opportunity to stress test our standards and our verification method. And this has actually led to updates of our standards, which are now for the benefit of technology providers, developers, and also regulators around the world. And when it comes to how we need to convince or who we need to convince of the floating wind potential, I think the most important are the policymakers. If the policymakers are convinced that the cost reduction and learning will come, and that they get confidence that the floating wind technology works, and they also understand the great benefits from this technology, they can set clear targets, open up areas, and provide the necessary incentives for floating wind.
Thank you very much, Magnus. Moving now to Wei, you oversee Mingyang's operations in Europe, and as a turbine manufacturer, there will be no shortage of demand as we hope to see more of the type of commercial project that we've already discussed, as well as a growing number of pilots and pre-commercial projects around the globe. Can you tell us a little bit about the considerations for wind turbine design and installation, which is specific to the floating wind concept? And for you, what are the challenges that lie ahead in terms of production and technical development to meet this expected demand?
Yeah, many thanks for the introduction and also the chance to join this really nice panel discussion. So regarding your questions, yeah, indeed, for the turbine manufacturers, it's indeed challenging to come to these floating wind areas, since originally all the turbines, of course, is designed for either for onshore or for the bottom fix, and now coming to the new trend of floating, and this indeed challenge our design, since, for instance, they might lead to a higher loads, for instance, for certain components, and also due to that, there's of the market currently, there's still a lot of different types of floaters, which also have different characteristics, which we are interact also with the turbine design. Yeah. So it means that for a demo project, for instance, the one we are going to deploy this year in China, so we actually put a lot of engineering effort to have optimal integration of our turbine with the floater. Of course, that is a kind of learning curve. I think each manufacturer needs to have that, from the first one to second one and to the third one maybe. But still, we see that if we get up the numbers of the installed numbers of the floating turbines, we need to have a unified or a certain number of unified floater, which could be somehow produced in a big number. And for that, we could also optimize our turbine for those kind of floaters, because nowadays we might have more than 20 different kind of turbine floater, but our turbine could not be optimal for all of them. Yeah, so we do see that in the future, in the next several years, the type of floater need to be reduced and to be optimized, and more integration with the turbine done, and so that the overall cost of the floating wind could be reduced, and which is the basis basically for the large commercial sized floating project. Yeah, so that is one part, and think the second part is that the turbine OEM and also the float design also need to work more closely together to have interchange in an early stage, especially when we now design a new turbine. So we need to also consider the application of the floating environment in our initial design. And for instance, with Equino or other developer, we could have very good input, so that we can avoid in a later stage we have some difficulties to adjust our turbine to the floating project. So I think that is also important, this early stage involvement between the developer, float designer, and also turbine manufacturer, to make sure that our next generation turbine big platform could also be used without a big change to the floating environment. So yeah, that's basically from the challenge of the design side. As we are headquartered in Asia, and recently also very good development in floating wind in Asian market, like in China, like in South Korea, like in Japan. So we are basically involved in all those kind of development. And as I mentioned, we are going to deploy the first floating demo in China, which would be the first one. And later on, there would be a lot of development in the areas I just mentioned. And in those areas, including China, there's also different characteristics compared with that in Europe. For instance, in China, not only for floating wind, also for bottom fixed, we have relatively low wind speed, for instance, and we have typhoon, which greatly challenge our design. Since on one hand, we need a bigger rotor, since we have lower wind, so in order to capture the same energy, we need a bigger rotor. But at the same time, we have the challenge of typhoon, which lead to a very high loads. So it's a difficult job, and those difficulties also applied for floating wind. So that's one part, and the second part is that there's also complex seabed conditions in Asia areas, for instance, China. So even for some water depths areas not so high, but still the application of floating wind is could be used because of the complex seabed condition, which asks for a shallow water floating solution, which is still not so well researched. I would say globally. So let's bring both chance and challenge of see from Asian market, but still I think it's really excited areas to be worked on, and with that we can explore much more potential of offshore wind. Yeah, thanks.
Thank you very much, Wei. And of course, DNV's own analysis of the markets does indeed demonstrate that we see huge potential in Southeast Asia, and among others for the reasons that you've just mentioned. So huge potential, as well as some technical challenges to overcome along the way. Thank you very much for that very interesting insight. Magnus, if I could turn again to you now. We've heard so far from our speakers about the work that the industry is doing to move floating wind forward, but we know from fixed offshore development that the input of policymakers will be essential. So can you give us a sense of the main actions that policymakers and regulators can take to help accelerate the development and the uptake of this technology?
Yeah, sure. Yes, so I can share some thoughts. So I think first, floating wind has some added risk in the current stage, and I think policymakers should do their best to at least remove the risk beyond the floating wind technology itself, having clear policies and framework and regulations, and also ideally harmonize this between markets so players can have better predictability, which also reduces risk. Another thing is to provide the financial incentives, which really is needed to achieve the steep learning curve for floating wind and the expected cost reduction. And the most important for floating wind now is to get the financial support for actual projects, so we can get the next round of wind farms into the water. But also support related to R&D activities is important. And the policymakers should also show the industry that they are in floating wind for the long run. Long-term floating wind targets will help establishing a dedicated supply chain. Without this, you will have players that are coming and going, and the risk of not getting the necessary cost reduction. We also believe that the policymaker can have a role to play in collaboration and standardization. So very country-specific regulations can halt the global development of floating wind. We really want the learnings from wind farms built in Asia towards Europe and vice versa. And last, I think floating wind is moving in a tremendous speed. We will see so much innovation and things changing over the next years. Policymakers should definitely allow for certainty to reduce risk, as mentioned earlier. We should also allow for flexibility. We will have a lot of innovation in the coming years, and we don't want the industry to be locked into non-optimal solutions.
Thank you very much, Magnus. And Sebastian, returning to you, Magnus has been talking there about the role of policy and regulation. And of course, Equinor has already had experience of that with the authorities in Scotland over that very first commercial project. So can you talk about that relationship and how important that was to making that project a success?
Sure, and building on what Magnus is saying, I think Highwind Scotland was the first of a kind, and so it was a kind of a close dialogue between the Scottish and the UK government and us on how to do it, and I think the eager and the willingness from Scotland and UK to be kind of a first mover on this was very important for us, and obviously the whole regulatory framework around Highwind Scotland with the rocks, etc., was a key enabler to do it. And I think that's where you need to strike the balance in a market context going forward. Is this, like Magnus say, you need innovation, you need optimal technology for this, but you also need to be conscious about your costs. So you need to work in parallel with kind of optimizing and innovating. You also need an innovation for cost reduction and industrialization. And in that context, you cannot probably have too many concepts going on too long in parallel. The market and the industry needs to gather around a few, what I would say, design principles, and so, as we've seen in bottom fixed. So that's an important thing with it. But on the other side, I think from a Hywind Scotland perspective and other markets, this whole coexistence debate that that exists with the offshore wind and fishery, etc., was extremely important and will be important going forward. That the government are kind of playing along and make sure to make the process as transparent and as predictable as possible. And I think by the consenting and the permitting will be important, because all of this is kind of part of de-risking a project that already, as Magnus said, is higher on cost than alternatives, but the world will need it. And if we need it ready when the world really will need the volumes, we need to de-risk it now. So we have, let's say, 5, 6, 7 years to really get down on cost by de-risking, and that's where the government plays an important role. And I think the what's happening now with the ScotWind round is an important example of how UK are following up from the Hywind Scotland and of course other offshore wind ambitions, where you will see a lot of the sites made available for the ScotWind route will be floating, and that's a very important step to actually show a pipeline, show a kind of a long-term ambition for building floating when you really will need the volumes a few years from now. So I think the learning and the kind of testing in Hywind Scotland was important to breed the ground for what's going to happen in the ScotWind round. And then, of course, the whole regulatory framework and support mechanism that would be needed in the kind of first commercial/pre-commercial projects will be an important policy making decision to make if you want to enable floating. So on that note, I think I leave it.
Thank you very much, Sebastian. We've heard some great insights from all of you already, and I'm going to conclude this part of the session by getting a perspective from each of you on the same question. So we've seen rapid early development of floating wind, and we've already mentioned some of the factors that need to be addressed to take it to the next level. But I'd like to hear from you, what are the critical factors in achieving the acceleration in the uptake of this technology? I'll start with you, Sebastian, then we'll move to Wei, and then finally Magnus. So Sebastian, your view on those critical factors to achieve acceleration.
Yeah, I think we touched upon them already, but let's try to summarize them. I think the critical factor is to make governments and industry and financial actors act together in a kind of consistent, coherent way, meaning that the government needs policy in place, they need the right regulatory framework, and they need to make areas available. And then secondly, industry needs to innovate, they need to be part of the risk sharing, and they need to go in and invest in this. And then thirdly, obviously the financial part of it needs to stand behind, and we see that coming now to finance this. And if those three kind of components can work together and make sure that we are on the right cost trajectory as we talked about, and that government will be transparent and predictable and have this pipeline of projects coming, so industry will see that you can actually invest for the future, not just a one-off, then I think we have a very strong coalition in building it. And of course we will build on whatever Bottom Fixed is doing. We'll build on the turbine, the development in turbines, and we will build on oil and gas experience from floating structures. So we have a lot of the technology and experience. We just need to put it together and scale it up so you get the competition and the cost reduction we need.
Thank you. Wei, your view on that question.
Yeah, many thanks. So from my perspective, the key element to scale up to commercial scale of the floating wind is essentially the cost. The cost not only for the components like turbines, like floaters, but also for the lifetime cost of the installation of the O&M. So especially for the later part, we still lack of experience, like how the operation maintenance would be cost, and also taking into consideration different kind of concept of floaters, and what does that mean for the maintenance and lifetime cost, and also of the whole systems. So we're still lacking of the experience of that, and that's put some difficulties to calculate the whole lifetime cost, and more essentially how to reduce that. So I think if we in 10 years or within 10 years, we could reach a similar LCOE as that of Bottom Fixed, so that we can finally scale up to commercial scale and to deploy an industrialized, let's say, turbines technology, and also plus the floater technologies. So that way we finally get that point to be a large-scaled commercial used floating wind. Yeah, thanks.
Thank you, Wei. And Magnus, that same question for you.
Yeah, thanks. So floating wind, I think, is proven, and we have talked a lot about that earlier today. But now I think the focus should be on optimizing and getting the necessary cost reduction. And I think this can be done by opening up areas. We have to have somewhere to build the next project, providing visibility to the industry by having clear targets for floating wind, so the supply chain can also invest and dedicate themselves for floating wind. And we need the necessary policies and financial incentives to really push floating down on the cost reduction trajectory. So I think it is echoing a lot of what both Wei and Sebastian has said related to floating wind.
Thank you, Magnus, and thank you to all our speakers today for what has been a very insightful and also thought-provoking discussion. I hope our speakers have provided you, our delegates, with the same sense of optimism that we have at DNV over this potentially revolutionary technology. And now it's your turn. We're delighted that our panelists and also Henrik Stiesdal will be joining for the Q&A session, and they're here for the next 30 minutes to give their answers to your questions today. So first, a bit of housekeeping. Please type any questions into the Q&A box, and then we can open it up to the floor. In fact, I'm going to take advantage of my position as moderator and ask the first question myself to Sebastian. Sebastian, we've talked a lot about the importance of these first projects to scale up floating offshore wind. And in fact, in Equinor, you're also scaling up because you're now moving to the Hywind Tampen project, following on from the success of the project off the coast of Scotland. So can you tell us a little bit on how Tampen is progressing?
Yeah, thank you, Lucy. Tampen is progressing well. We have even with the COVID situation, we are on schedule and are planning for really a COD in 2022. And the importance of this is that between the demo and Hywind Scotland, it was roughly 10 years, and now between Hywind Scotland and this, it's much less. And I think that's an important thing, that we see that the market are really progressing. Secondly, it is almost 3 times bigger than Hywind Scotland, so we are in a way scaling up now as a stepping stone. And then maybe the most important, we are aiming and on track, I think, for a 40% cost reduction per megawatt installed, and that 40% cost reduction is really the proof in the pudding. That shows that we can get down to where we need to be in floating in a few years from now. And then of course, very important, we are integrating this with oil and gas. Meaning we are replacing gas turbines to reduce the CO2 emissions from the operation there, and that in itself, from a technology perspective, is important because you integrate into an island mode, and this makes it also available and relevant for other concepts. If you think about hydrogen in the future, if you think about, in a way, standalone assets that are not connected to the grid. So it's a little bit of a kinder egg for us, both in terms of cost reduction and stepping up the scale and innovation.
Thank you very much, Sebastian. And actually, that first question that we've got is also about how we can streamline costs in terms of maintenance, and perhaps I'll stick with you for that one. So what are the most economic options for maintenance? And I would perhaps link that to a later question we had that was also related to maintenance, about what has been the experience in actually towing wind turbines back to ports for maintenance. So perhaps you could answer those 2 questions about the options for maintenance and how maintenance is developing for these projects.
I mean, Magnus touched upon it in his presentation that we will still need innovation. I think this is one of the areas where we will need constant innovation to reduce cost and make it more efficient. And obviously, to tow it back to shore is probably more expensive than doing it out on the offshore. But still, we are constantly working on this, and I think there's 2-3 components. Obviously, we need to piggyback on what's happening on bottom fixed and learn from that. Then there are some specificities with floating that you cannot fix, like it is floating. It's not fixed. And I think one of the things, and Henrik can probably talk much more about it, is we need to work on predictive maintenance. We need to really optimize the system for that. We need technology on how to do unmanned operations out there, and we need to avoid the heavy component as much as possible. And I think with all of those kind of efforts together, we will manage it, and then I'm pretty sure you will find vessels in 5 to 10 years from now that can do also heavy component changes. But by the way, the Hywind demo has been there since 2009, and we haven't been needed to take it to shore at all. So in a way, it's proven that this is not a huge problem in itself. But of course, you need to find a solution to the heavy component part of it.
Thanks very much, Sebastian. I'll take the next question to Henrik. Henrik, there was a question about, in particular, about your own design for a floater. And can you tell us a little bit about that?
Yeah, sure. I just want to add a thing to what Sebastian just mentioned, that just as a fingertip, just to get a fingertip feeling of the O&M heavy component maintenance requirement, I think the consensus today is that you should expect in a large fleet that about 50% of the turbines over a 30-year period will need one main component replacement. So, of course, I'm happy that Hywind demo from 2009 didn't do it yet, but in the long run, this sort of half of the turbines will need it sometime during their life. It's probably a good yardstick to do the planning of major interventions. My own design is the result of as you could say, a thought process that has to do with how do we accelerate industrialization. In tendency, when you do big new structures like what we do in floating offshore wind, you tend to fall in love with your own idea, and you want to do a certain configuration because you persuaded yourself and your colleagues, they persuaded you that it is the best way to do it. I actually tried to do it with a different mindset that basically said it has to be able to be produced in factories out of the simple consideration that cheap stuff is made in factories. There's a reason why you don't have movable tower factories that move around with wind farms onshore, even though towers are expensive to move around. There's a reason why you don't have movable blade factories and so on. It's because an industrial setup needs to be done in a systematic manner in a factory. So I basically set out simply, should we say, taking a firm stand on the opinion that things needed to be no larger than that they could still be made in factories doing, well, quite large stuff. And such factories would be tower factories. Because tower factories are actually very good at what they do. Wind turbine towers are most likely the most cost competitive big steel structure you can find anywhere in the world. Because they are done in competition between different tower manufacturers. They have the cost pressure, and they are the result of a long learning curve, and they have got really, really good at what they are doing. So my design basically takes as a starting point that in order to make it cheap, I simply use equipment that can be made in tower factories. And of course, then it requires that you have an assembly method so that you drive or ship those components to the port of embarkation, assemble your foundation there. And that is what a lot of the effort goes into. That is to make structurally sound assembly methods. So this is kind of what I'm working on. That is to say, we need to accelerate industrialization. Things have to be made in factories. Let's see, how do we do that?
Thank you very much. Fascinating. And of course, important element of reducing the cost of floating wind. The next question I'll direct to Wei. Wei, I think we can hear you, but we can't see you. But anyway, I can see that you're on. So the first question was about how suitable are onshore wind turbines for being repurposed for floating. And you did actually address that during the panel session, but perhaps you could just reinforce a couple of points about the needs for adaptation of onshore turbines for floating. And Perhaps also there was a question about the key requirements that Mingyang have towards a floater. So those are two very similar questions. Perhaps you could address those.
Many thanks. So I hope you can hear me. So due to some reason, my camera does not work. But anyway, I think these are quite good questions. I think the first one is regarding the onshore turbine or bottom fixed offshore turbine to floating. So I would say that at least we need to do some software adaptations like the controller tuning. And of course, the tower itself is always site specific, as that also the case for the bottom fixed offshore. So in any case, we need to adapt our controller as a minimum for software and also the tower as a minimum for the hardware. And then, of course, we will see as a turbine OEM, we are trying to avoid major modifications for our turbine because of the cost, because of timelines. So we will try to, we will do the, for instance, a load evaluation again to see if all our components are still in the design envelope for that specific floating environment. So if that is the case, then we do not actually need to modify it and not in our, especially for our rotor nonsense assembly. But in some case, because the trend of the turbine design is that we are quite near to the boundary of our design because we want to reduce the cost. We are scaled up our platform to higher rated power. So for some cases, we might still difficulties to directly apply our onshore or bottom fixed turbine to some specific floating environment. Then we might need to adjust some part of our components, like bearings, like some components, like our lubrication system, for instance. So so there could be some modifications depending on the site. So that's one part. I think on the other part, we will also actively consider the floating environment in our new platform design. So we would already consider, for instance, a higher acceleration in nacelle in our design for the new turbine platforms, and also in the load envelopes, we will more consider reserve, for instance, in our bearings. So that is also another part which will contribute in the future that our turbine could apply both in bottom fixed and the floating environment. And yeah, I think that is what from my perspective for the first question. Yeah.
Okay, thank you. And I guess there was attached to the second question about which key requirements you have for a floater. There was a rather perhaps a political question about if Mingyang has a favorite floater.
Yeah, so no, we do not have a favorite floater. So because we do see that now we have a lot of different types of the floater under development, and also according to different sites. So like the water depths, like the alert environment, and different types of floater is also required for different sites. That is it's also maybe also the case for bottom fix. If depend on what the depths, which types of foundation need to be applied. So and on the other side also the materials of foundations also depending on the industrialization of different areas. Some place might be more suitable for steel industry, then the material should be steel, and in some part of the world the beton, the concrete material might be more preferred because of the local industrialization's characteristics. So I think, but we as OEM, we do prefer that we if we could reduce the type of the foundation so that we do not have so many different types because different types of foundation means different characteristics, means different dynamics. Which also means for turbine OEM to have more work to do, let's say, for different to integrate with different type of floater. So we do hope that the types of the floater could be reduced in the next 5-10 years to be several. I would not say that there will be only one type, so but maybe less than or around 5 or 6, so that we could consider that already that kind of floater design, our turbine design, which could further optimize our design process and also in total to reduce the LCOE. Yeah.
Thanks very much, Wei. There are lots more questions coming in, but we are running out of time for this session. So I'm just going to take one final question for you, Magnus. And I see there were quite a lot of thumbs up for this one. And you did address it during the panel session, but perhaps you could tell us what would be the biggest game changer to improve project economics, reduce the LCOE, and also which will convince financiers to invest?
Yeah, thanks. It's a good question. I think the next step is basically industrialization. We have to. Today are been just a few units, and now we kind of have to start adapting to building many quickly, and then it's several approaches to that. It can be more of having fabrication yards that can do it. We see, for example, yards in Korea that basically are sending out super tankers every other week. So there, of course, they have some capabilities, but of course those vary around the world. So it's a little bit about kind of the fabrication facilities of the yard, but it's also it can also be on the foundation design as well, and also a combination such as the Stiesdal's combination, which is more about not using the kind of those the fancy yards. So, but I think the focus is that it's about industrialization, about serial producing and making things quickly and efficient. And which will convince the financiers to invest. I think we seek a lot of interest from financiers. So I think they are quite ready to jump in these projects. But we as a company as well, we are just trying to comfort them, seeing that this works. There, of course, are risks, but they can be managed, and that's also proven by the projects and pilots that are installed today. And also, we also try to, both with this as a technical advisor, but also as well as a certification body and classification body as well, to try to give confidence to those projects that they will work. So in that way, we do some part, but I think also the extremely good things that, for example, the first one out, for example, Equinor has done is been giving a lot of confidence to the financiers. So
Thank you. And I'd like to thank all the panelists for what has been a really fascinating session, and has obviously provoked a lot of questions. We haven't had time to go through all of them. For all those who've been listening, this will be recorded and available, so you can watch again, and a lot of those questions were actually addressed during the panel session. So with that, we move on to the Meet the Expert session, and that is going to be led by Magnus. And so Magnus, over to you for the Meet the Expert session.
Okay, thanks a lot for continuing in this session and participating in the Meet the Expert session. So we are now bringing in some technical experts from DNVGL, and we will go through the questions. So please issue questions as well as upload questions that you want us to look at. But first, I'd like to introduce the experts we have in this call. So I have our floating wind certification director, Timon Argiradis, who is our director for certification for floating offshore wind, and follow up the certification activities we do related to floating wind around the world. Including this is also developing of standards and recommended practices and service documents, as well as following up R&D activities related to floating wind. We have also our mooring expert, Alex Argyros, who is a lead naval architect and also technical authority for moorings for the Noble Denton Marine Service Department, specializing in design and approval of mooring systems used in floating wind, wave energy, tidal, and oil and gas applications. We have, let's see if you're sharing here, our cable expert, Oddrun. We have joined DNVGL since 1999 and worked with dynamic power cables, both for oil and gas and renewable market. Her main expertise is the structural and mechanical part of both static and dynamic cables. We'll see if she can join in later. We also have our floating wind design expert, Ben Child. So Ben is the lead for floating wind energy within Turbine Engineering Service, coordinating research, business development, and strategy in this area. He's also the team lead for a group of 10 interdisciplinary engineers working with loads, aerodynamics, and control. So, all right, so let's dive into the questions. I think one of maybe the first question here, and maybe we'll do to Kimon. It was mentioned that motion control enables stabilization in high wind speed. Can floating wind be possible and safe in high cyclone areas around the world?
I would say the answer is yes, but. So I would say motion control systems, we see them in floating wind turbines, and they can be a very big gain on the design. So you can use the big rotor to stabilize the turbine, and this is in the whole system. And this is used already in some cases, and we have it even already in the standards. Now, going to the cyclone conditions, there I would say it is always a matter how you design to. And we have seen earlier today, this was in the ACE JIP session, that the main thing is how to predict what wind speed, what wave height, what storm surge to design for in the side. If you have those, I think this is definitely positive and
it works.
Possible to design for
yes.
For cyclone conditions. Of course, Wei Chen mentioned earlier, some minutes earlier, it is a matter of optimization compared to the between operation and extreme loading of the wind turbine.
Thanks a lot. I see it's another question here. Have you any knowledge of a floating wind turbine being towed to harbor for service and repair? I can try to answer that myself. From my knowledge, I haven't seen that happening in an operational floating wind farm. Of course, there are so many, but of course, it's been kind of decommissioned and recommissioned turbines, and there's so experience from that. And for first wind float prototype has been reissued at another floating wind farm, so there's some experience there. But I think in a operational wind farm, I am not aware of any experience of that. Let me see if there's another. I think maybe this is for the cloud. Is he here? Yeah. Could you please give some more color on the motion control systems currently implemented? And what those are available to be developed. So, how is this motion control system working for floating wind, and are there any changes and development there?
Sure. Okay. Well, I think the main kind of technique that's used in this area that Henrik was referring to earlier is primarily with the controller on the turbine. So the issue being that when we have large motions of the platform, the turbine itself sees a higher apparent wind speed, and so the blades pitch towards feather, which in turn gives a lower aerodynamic damping, and that accentuates the motion. So what you can do then is to just address this via the control algorithm in the turbine itself, and we can kind of slow down these kind of negative interactions which accentuate themselves. But there's all sorts of other kind of control techniques that are also possible. There are platform control algorithms that are possible, where you can use things like mass spring dampers in order to get a better response for the platform in particular environmental conditions. So all of this is a kind of active area of research, really, to kind of bring all of the control together into something which will enable the turbine to do what it does best, which is basically to have fairly stable operation in as high wind speeds as it can. But as Henrik mentioned, the basic technology is already there. It just requires particular attention when it comes to the control design. And I should also mention that in order to be able to do this, to get these effects that happen in reality, we need a kind of coupled simulation where the platform dynamics affects the turbine and vice versa. Otherwise, we won't see these effects and we won't be able to solve them.
Thanks a lot. That's a very good answer. And Oddrun, if you are here, I'm just wondering what if you can. The question is if in the bottom fixed industry we have quite a lot of experience with cables, but what are the main things that needs to be considered when you are going to floating wind and need dynamic cables?
Well, can you hear me?
Yes.
Yes, that's good. Sorry, I had some technical issues. Floating wind require dynamic cables, and one of the main challenges, as I see, is the dynamic high voltage cables needing water barrier, for instance, where fatigue becomes an issue. So the dynamic cables are for sure more fatigue prone than the bottom fixed. But there's a lot of experience from oil and gas, of course, when it comes to good solutions for the configuration and things. But material and fatigue issues related to dynamic cables is a challenge.
Okay. No, thanks a lot on that. I think this is a question maybe answered with caution, maybe, but maybe for you, Timon, are there any particular designs you think will win over others in the future for floating wind? I think there was a lot of talk about standardization and minimizing the number of concepts. So spar versus semi versus tension leg. Any thoughts there?
So, okay, now, can you hear me now? Yeah, I hope. So, I think we are not there yet. The optimum floater for floating wind technology. We are going to see more spars, more semi-subs and TLPs coming up, and barges or pontoon-like structures. And the optimum depends a little bit on the site and on the regime you have. So different water depths may have advantage for different structures. This is one thing. The other thing has to do also with the manufacturing constraints you have. We're going to see different manufacturing constraints, for example, for semi-subs than for spars. These are the two main we are seeing today with the high winds or the wind floater designs. And further peculiarities, and both have the right to be there as they are. So you can't put a spar in 50 meters water depth. This is not going to work probably, or it's going to be a very short one. The same applies, it has a simplicity. Around for the semi-sub and the material you are going to use. So we are not through yet. Maybe in 10 years' time, when we have the more than 20 gigawatts installed, we are going to find a way. But I say it is dependent on the site, and there is still room for optimization there. I have no favorite design.
And if I could add a little bit on that, I think I can see the desire to kind of narrow down the field in this area. and especially when you're talking about turbine manufacturers who are keen to be able to make turbines for floating and want to do optimizations. But I think the idea of stifling innovation in what is still quite a sort of young field relatively wins out for me primarily. Also because I think the narrowing of the field, it will happen naturally. You will get the leading concepts, the ones that have been deployed for the longest and can demonstrate their cost of energy, and things will naturally form around those types of concepts. And then it's up to the challengers in the industry, the new R&D, to prove them against that benchmark. And if they are indeed better, then they'll rise to the surface. But if they're not, then the industry will continue to converge. So I think we have to just have a little bit of patience here and to see the market evolve.
Okay. No, thanks. Yeah, I know we see their new concept coming up every day, and there are probably more than 40 concepts. So yeah, but it's still a race, still a competition, and there's kind of no clear winner and no clear favorites. So this interesting years to come. But yeah, it's good points related to the turbine and their challenges. Just a little question on the side here, Alex. Do you have any thoughts on kind of the mooring systems you might see in the future of floating wind? Now we typically have three mooring lines and 3 anchors, and maybe fluke anchors has been the most used solution. But how do you see kind of the future of moorings for floating wind?
Yeah, sure. There was actually a question on shared anchors, so maybe I'll try to cover that with this answer. I think of course shared mooring systems is one innovation, particular to floating wind, and the benefit there is ultimately cost reduction, is having fewer anchors and installing fewer anchors. For example, if using suction anchors, which are not necessarily that cheap, if you can connect 3 lines to an anchor or more, then that potentially is a significant cost saving. But when we're referring to shared mooring, let's call it shared station keeping, there's really 2 types. There's shared anchors, where you have multiple anchors, multiple lines going to one anchor point, so there can be 3 or 4 different pad eyes on the same anchor. And you can also have shared mooring lines, where you're using a conventional anchor like a drag anchor, and then you have a mid-water connection like a buoy, where you can create a web of systems. So there are different challenges with those. So for example, with the shared anchors, the challenges, this shared suction anchors, for example, the challenges are different load paths, and geotechnical engineering becomes a bit more complicated. The structural engineering of the anchor itself becomes more complicated because you have multiple load paths, and if you lose a line, then you change the load path into the anchor itself. And with challenges with shared mooring lines is, if you've got a fully interconnected system, then each turbine can depend on this integrity of the adjacent mooring system, and therefore you can get potentially unzipping effects if you lose one line, and that can cause larger failure into the whole farm. Other areas of novel, to answer your question, is novelties, of course, materials. And we're seeing fiber rope, much more use of fiber rope in floating wind, and perhaps floating wind offers the right platform in order to test novel materials like nylon, whereas oil and gas operators were a bit reluctant to use such materials because of the high potential impact of environmental impact, but also like cost implications of like oil production units. So we're seeing nylon used a lot, and that's quite a strong mooring component, but also it's quite soft. It has a lot of compliance, which means by having a soft stiffness, you can reduce loads into your mooring system. And if you reduce loads, you reduce anchor size, you reduce pad sizes on the structure itself. So you reduce steel, so it's a lot of impact to cost, reduction to cost. And then the final thing is on the integrity management side. I think Henrik mentioned the importance of remote monitoring and unmanned monitoring. So integrating monitoring systems with a reliable risk-based inspection plan is really essential for floating wind.
Okay. No, thanks a lot. And yeah, it's very interesting. At least also the operational phase you go into now. I think floating wind, we have built it, but now we're going to operate it. I don't know. Maybe I can also get that question to Kimon. Do you see anything of innovations and things that we'll see in the operational phase on how to reduce costs in the operational phase? Perhaps also feeding it back to the design.
Yeah, so we see there are many possibilities for improving. Of course, digitalization is a huge thing one can consider, and then, of course, having monitoring and data collection and use of this data, for example, to optimize the controller continuously during operation. This is one thing. So this is something you can optimize. The other thing, of course, is that all the methods we have. So predictive maintenance is prediction of maintenance, and risk-based maintenance is one very big thing one can apply using monitoring systems. And we have the possibility to make even monitoring of the mooring system. We have to look about accelerations on the system, and then based on that, using digital twins, we have an optimization of the maintenance. So that maintenance intervals can get bigger, and this is the one thing. And on the other hand, more focused. The number of visits you have to do offshore. Then we have other developments, for example, in the cable. So if we want to tow a floater to land, we've seen this option, or this option is from time to time discussed. So you have to disconnect cables. But we see a development, for example, a possibility to have connectors. We make connectors, for example, for the cables you can use for the high power needed. This is a development which is, I think, ongoing. And of course, we have then the development on all the system access systems. So you can imagine that if a boat is coming to a floating wind turbine, you have two moving objects, and you want to transfer personnel from the one to the other. So this means that this is something where further development is needed and is going to happen. So this is where we go to the operation and maintenance. The other developments, especially in the design, optimization of the design, materials to be used, where we see, as Alex mentioned, nylon for moorings, offer P structures for buoyancy structures, and so on to be used in the designs, and all these things.
I think
so there is a huge possibility there.
I think another factor.
Ben has also other points to add in that.
Yeah, I think another factor on the design side, as you were mentioning, really a kind of more hidden one is to do with the design process itself. So I think we need kind of innovations and different ways of thinking to conduct the design process. We heard earlier about the kind of the integration risk of different backgrounds, different partners using different tools and different methods. And I think really the point of getting to a common understanding and getting a consistent analysis of all of that is actually quite a difficult achievement in any consortium, let alone the kind of intellectual property issues that you sometimes get in the sharing of information. So I think innovation around the tools that we use and the kind of shapes of consortiums and the kind of flow of information between partners really has the capacity to very much compress that kind of early design stage and get to kind of whole system optimization much faster.
Yeah. Okay. Well, thanks a lot. It was very useful. And just a question to Oddrun here. It's a question on how do you measure fatigue in how do you monitor fatigue in cables? Is it visual? Is it temperature? Or is it listen to a bang? So there's two here about questions related to this fatigue in cables. I wonder if you can elaborate on that.
That's of course a good question. There are often fiber optics in these cables, so there are ways of doing some measurements, and I think you could use temperature. But what you usually do is to design them to have acceptable fatigue life during the service life. It's not easy to monitor the fatigue within these complex cross sections in a way. So do a proper design and do proper analysis, fatigue analysis up front. But then I need to mention that the cable design often come a little bit late in the development of a floating wind farm, and that it need to also consider the same coupled motion analysis as mentioned for the turbine, the floater, and the mooring system. And to get the proper loading in the cable, you also need to consider all these loading on the whole turbine to get a good assessment of the fatigue capacity or the fatigue response in the cable. And I also want to add that one of the things that is still under development and that has still not been we haven't seen it in a project yet, that is a substation. You need to have a reliable way for transmitting the power that you have generated. Floating substations it's under development, but that is something that we don't have that kind of field experience with yet, and those will require this high voltage cable for dynamic application that is also worked on, but it's not been. We have very limited experience with it.
Yeah, thanks. Yeah, that's an interesting point there as well on these dynamic cables. I think we need to qualify dynamic cables for this 220 kV up voltage levels. So that is something I think the industry is looking at. There's several questions here relating to, and maybe I direct this to Ben. There's several questions here about combining floating wind with wave power. It'd be great if you kind of share your view related to that and opportunity challenges and maybe opportunities regards to that.
Yeah, sure. So I think this is one classic area where there is still innovation in this particular industry, and I think we absolutely need to keep that. And the potential advantages being sharing of export cables and operations and maintenance, and even down to theoretically providing more of a sort of sheltered area for boats to rest when they're performing O&M. Proponents would say. So I think it has to be explored in the grand scheme of everything else that's out there already, and who knows what other kind of combinations of technologies that might prove successful. We've seen with Hywind Tampen the combination of oil and gas and floating offshore wind. There may yet be others which prove that winning combination, even if not long term, then to enable a kind of a demonstration and to provide something that's realistic and meaningful in this kind of first demonstration phase. So I think it absolutely has to be something to be explored. and look forward to more innovations in this area alongside that.
Yeah, no, it's very interesting. No, I guess it reflects the things we discussed earlier, that it's a lot of innovation, a lot of things coming up of concepts, and things hasn't settled yet. So I think there was another question here related to standard, and I think this is natural to address to you, Timon. Is there a standard, and in which standard that addresses the requirements for an integrated control system covering the turbine and the floating platform?
Yeah. So we have some input about integrated control systems in our standards in the ST 0119 standard, which is the main standard for floating wind turbines. We have a section where we talk about the requirements for the control system and for the consideration of floater control systems and their combination. We have also made some work in the development of a recommended practice for the coupled analysis of floating wind turbines. The practice 286, I think, yes. Where we made several analyses of floating wind turbines, and we looked about the effect of coupled control system. So this is found its way in the standards. There are some general rules what to consider from the safety point of view and what to consider from the design point of view for optimized design. Saying that, there is still a lot of room for development there because we are at the very beginning of this. We have the control systems, which are, for example, used, for example, to ballast a floater, which is in use already, and this is considered in the standard. On the other hand, we have also the more complex controls that are connected both with the ballasting of the turbine and the turbine controller to provide, for example, some active damping, as Ben was told earlier. And then, of course, this can even be connected with wind farm control systems, which control the behavior of the turbines in a wind farm. So then the systems get complex. In principle, we have the requirements, which are the general requirements for wind farms and the special requirements for floater control system. To repeat it, there is still room for development there. We are far from being at the end.
Okay. No, thanks. I think it's a good question. I think maybe just following up on that, what are kind of the updates related to standards that you are working on, or that you might see in the future? I kind of wanted if you
yes.
do that really briefly.
Yes, so we have just now worked in 2020 in a first update of our standard, where we reviewed the floating stability part and made also some clarifications in parts like air gap and the safety factors to be used in some cases, ALS cases, short. But this is not the end. We are just starting now the next review round, and we are going to try to start a joint industry project where we look about the mooring design and calibration of safety factors for mooring as a continuation of the normal JIP, which was made in the for FPSOs, for example. And this is one step. We want to look on the development of requirements for floating concrete structures, because there are some special consideration when it comes to tightness of the floater. And gap-wise allowed and the coverage allowed for concrete structures. My personal view is, out of the update we just made, we would like to make even a joint industry project for floating stability, where we can really look about the dynamic stability requirements in a fresh way, and not borrow the requirements from the classic naval architecture. So, because we see a different approach here. So these are some ideas we have with first the joint industry project on the mooring safety factor calibration.
Thanks a lot on that. There are several questions here related to cost, and one question is the foundation cost for floating wind versus bottom fixed, and also cost in general in floating wind versus bottom fixed. I can on the foundation part. So there's a cost premium for floating wind. Having to have a monopile for a 8 megawatt turbine, you might go, or 10 megawatt, you can maybe go below 1,000 tons. Typically for floating, you will go for 2,000 tons for just a floater, and then you will have the mooring systems and anchors in addition. So you have more material, and also some of those material components might also be more complicated to fabricate. So there is on the foundation there is a cost premium, and that is said when there's also basically all floaters can be identical on the wind farm, and you can also maybe look into several wind farms as well has identical foundations, and then you can really start to produce them and go into car manufacturing type of methodology and really produce the low cost. So the cost will go lower, but I think we still will have a premium for floating wind in a way that it will cost a little bit more than at least the best bottom fixed wind farms. So I think that's the main difference between floating wind and bottom fixed. There's minor differences on them, and of course some differences related to cables, basically because you have longer cables, but you also have different cables because they need to allow for the dynamic motions and the movements of the floater. I think I wonder if I can maybe direct it to Ben. What do you think from your side? What do you think is the most important R&D that needs to be done for floating wind?
Yeah, sure. Well, I think it's got a lot to do with platform cost, really, and that's a large component of that comes down to capex. So it's in terms of reducing the amount of steel that has to be used, and I think really the key to be able to do that optimization is to have this kind of like really tight connection between the characteristics of the turbine and the characteristics of the floater. So we've seen it be quite difficult sometimes to get that flow of information working right. Sometimes turbine manufacturers may even be reluctant to pass on details of the mass of their turbine to the platform manufacturer at early stages. So I think really it's about providing a framework to get that flow of information working, so that we can really sort of optimize the whole system in a coupled way. And ultimately, there may be some modifications that can be made to the turbine to enable that reduction in mass of the platform. But I think this is clearly going to be something that's difficult with the array of different platform concepts that are out there, as we discussed earlier. But I'm hopeful that as the turbine OEMs learn more about the different platform types and the different characteristics, there will start to be a few parameters and a few kind of key things that get known that can be adjusted, so that this kind of optimization can happen in a very specific, limited way in the turbine in the early stages, way before any kind of platform-specific turbines are designed. So I think these are the first baby steps towards system optimization, but there are those things that we can start to be looking at now, and really sort of driving down the cost of the platforms.
Thanks a lot. I think we can we are over time, but I think we can stay in for 5-10 minutes more since there's so many questions. We can keep it going. And I just one question here, a bit on the details here, but and later to you, Alex. Can we have only 3 mooring lines for floaters? Do we need additional margin on mean breaking load?
So yeah, I think the answer is yes. It's we've got that in the standard in ST0119, where there's a system without redundancy. You require a higher consequence class to account for the risk of potential collision, and I guess also for the fact that it's not protecting the cable as much because of the large offset you'll get when you lose one of the 3 mooring lines. That is, yeah, I think that's currently what is in the standard. I would say on top of that, it's always good to think about the long-term integrity of a mooring system, whether you have 3, 6, or 12 lines. What we've learned from the oil and gas sector is that the relatively high rate of failure of mooring systems is due to degradation mechanisms and also in service, but also due to installation. And I guess floating wind does pose a challenge here. If you're installing 50 turbines, can you ensure the same level of installation on all 50 turbines? So there's a stronger emphasis on the need for better installation, better in-service integrity management, because at least that's the reason why moorings have failed in the oil and gas sector, not because they've been overloaded in general. So that's important for mooring designers to keep in mind, I think.
Okay. Thanks on that. Maybe another question for Kimon here. I know you're also working with following up things happening in other markets in Asia as well. So how many years do you think we will need to get mass production of floating wind at the same rhythm as bottom fixed?
I have not the numbers of what we have. DNV has DNV in its energy technology outlook. We talk about 250 gigawatt in 2050, and definitively some gigawatt already installed in 10 years. I would not say that it is going to be in 5 years. 10 years, I hope, and I'm convinced we are going to have mass production. So it's going to take its time. Develop a project. It's not an easy story. You need 5-7 years to develop a project from zero to have the turbines installed. There are many loops to be done, many challenges to be taken. But if we see now the prospects we have now and what we see to be developed in countries like in Europe, UK, France, Norway, or we see in Asia, or we see also projects to be developed in China, Korea, Japan, Taiwan now. So this is something where I see you need to make mass production if you want to be successful. There is no way not to do it. And I think in 10 years' time, we are going to say that it's not really fully established, but we are going to have at least some spots for production of floaters.
Great. Thanks a lot. That was very interesting. Yeah, I think we need to round off. We are all over our time, but it was so many good questions. So it's been really fun to discuss the floating wind with you and also with the experts. So I will thank a lot for you who has been attending this, and also a lot for our experts. So we are available through this the virtual booth as well as through the platform. If you have any questions and we have not been able to guess your questions, please reach out and we'll do our best to answer them. So thanks a lot, and hope you enjoy the rest of the events that are going to go for the next days.
Thank you very much.
Thank you. Thank you. Bye-bye.